We saw Markov chain, saw that it is a special kind of stochastic process, slightly more general than random variables being independent. More specifically, a sequence of random variables were called a stochastic process. We saw that a very specific case of it was Markov chain, specified by this particular property, that if I look at the value of the k plus 1th random variable conditioned on the variables before, we can say that it only depends on the value of the kth random variable. So for a general stochastic process, this thing will depend on all the random variables, this expression. But for a Markov property, it only depends on the kth random variable. You can think of it k as the present. What happened in the future depends on the present random variable. It encodes whatever has happened in the past. So this was the Markov property, and we also assumed that the Markov chain is going to be homogeneous. That means this transition probability does not depend on time. So where xk plus 1 and xk are some elements of the state space. Remember, for a stochastic process, the state space does not change. And then this becomes a homogeneous Markov chain. And we said that we will be only looking at homogeneous Markov chains. It turned out that a homogeneous Markov chain can be specified simply by two things: initial distribution and the transition matrix. The initial distribution was the probability of x0 being in different set I for all I element of S, and transition matrix was this set of probabilities. So probability x1 is equal to j given x0 is equal to I, and this we denoted by a matrix Tij. This was called a transition matrix. There is an easier way to represent this as a graph. So if I just make my state space as vertices of a graph, I can connect them with transition probability. Let's say my initial distribution, let's call it the vector mu. This is a vector with cardinality of s many constraints. So it tells you the probability at every point in the state space. This is mu1, this is mu2, mu3, this is the initial probability. And then there can be transition probabilities which will satisfy something. So let's say from 1, I go to 2 with probability half and go to 4 with probability half. So similarly, I can define this. So from 3 to 2, this will become the transition matrix probability T32. This will become T23 and so on. So this is how I can represent a Markov chain. So my initial distribution, I will just define it as mu0. This is time step 0. And then I want to see how a Markov chain evolves. That means what is the probability distribution after 1 time step, after 2 time steps, after t time steps. This is what we are interested in. And we will see that a Markov chain has a lot of structure. We can actually figure out what happens in the long run. We will see an application also in the next. Let's take an example. So if my transition matrix was this is a very simple Markov chain. It has two states, call them A and B. This does not specify the initial distribution. Let's say my mu is half and half. So I have half probability to be here, half probability to be here. And then with probability 1 from A to B, I move. And then from B to A, probability 1. So this is the graph which will represent this transition matrix and this initial probability. Let's define mu t to be the state at time t. Mu t I will be the probability of being in state I at time t. So let's start with the most simple case. Can we figure out what mu1 is? Remember, we are given mu0 and we are given the transition probability, the transition matrix. It will be easier if I just represent my transition matrix with letter M so that there is no confusion with the transpose. For now, this is our transition matrix. I'm just changing the name for the ease of notation. What is my mu1? From the picture, it's kind of clear that I have to go to some state. Let's say I would have gone from some other state space, correct? If I want to say mu1I, this is the probability that I start in some other state J and reach I in the next step. So this is the probability that I was in J, then moved to I, and I have to multiply with the probability that I started with state. And you notice that both of these quantities I know in terms of mu0 and m. So this becomes summation over j element of S mji mu0. And if you look at it keenly, you will see that if I look at it for all possible states I, this is actually giving me a vector equation, which is mu1 is mu0 times. How about mu2? I would say that again, there has to be some state. We are at state for the time step 1. Probability x2 is equal to j, given x0 is equal to I, it should depend on some intermediate state u element of S. It becomes probability x1 equal to mu given x0 equal to I multiplied by probability x2 equal to j given x1 is equal to u. And again, you can see it that this is basically multiplying as a matrix. I will let you stare at it for a while and you will realize that there is a very simple way to write the state after t time steps. So we saw that mu1 transpose was mu0 transpose multiplied by n. Then if we do it for 2 time steps, it becomes m square. And in the assignment, you will prove that after n time steps, the state can just be written as this multiplication. And this formally proves what we have been saying before, that my state in future is completely determined by just the initial distribution and transition matrix. So now we have a very nice way to say what happens in a Markov chain, how the state evolves. But we have been talking about a strong structural property. Let me just talk about it. What is the strong structural property? It will be very surprising if I say that the behavior of the Markov chain does not depend on how you start. Seems very weird to you, I'm sure. I will say that it actually don't even depend on mu. Long time behavior of the Markov chain only depends on the transition matrix. This might seem surprising, and this is not entirely true. But let's see when is it true. So again, what I'm going to say is that you remember that a Markov chain has these transition probabilities and then some initial state. And if I evolve it for a long time, so I'm looking at the state mu n as n tends to infinity. Claim is final state does not depend upon, this is not going to be complete. I have to say under some restriction, and these restrictions are specified by something called a regular mark. The question might be, do we need some restrictions? Can it happen that whatever be the starting state, I will always end up in the same state in the long run? The mu n kind of tends to some fixed state, W, as n tends to infinity. Can it happen for all Markov chains? And it's easy to see that there are these trivial cases when this cut cannot happen. Why do we need some restriction? That is because we can have Markov chains having two set of vertices which are not even connected. So something like this, if this is a Markov chain, there's a single Markov chain, then what happens is that if I start on the left side, then I will stay on the left side. If I start on the right side, then I will stay on the right side. So this kind of Markov chain will not converge to the same distribution. There is another case. Let's say this Markov chain, which we have already seen. So again, if I look at even time steps, I will be on the right side. If I look at odd steps, I will be on the left side. In these cases, we cannot converge to a. Barring these exceptions, we can define something which is called a regular Markov chain. What is a Markov chain? It will remove these trivial possibilities. It will put just a simple constraint in some sense that every vertex there is a probability of going from every state to every state, and there is some probability of staying at your own state also. So taking care of both of these things, we will define regular Markov chain as something such that there exists an M for which, if I look at the ijth entry of M to the capital M, it is greater than 0 for all I comma j in my states. It is important to remember the order of quantifiers here. It is saying that there exists a single M. It could be very big, I don't care, but there is a single M. When I look at that single M, every entry of M to the M to the small m, is non-zero and positive. If I start with positive entries, then forward it will remain positive. So important thing is that every entry is non-zero. Just with the simple restriction, which is true for almost all natural Markov chains, you will see that we will be able to prove that it converges to a fixed distribution. We will define it more formally later, but this fixed distribution will be called a stationary distribution. So you start with any state of your liking, but if you run the Markov chain long enough, it will converge to a fixed distribution. This only happens for regular Markov. It should surprise you. To prove this goal, we will start with a Markov chain M, which is regular. So that means we have small m such that this quantity is greater than 0 for all I comma j. What we want to prove is that there exists a vector W such that W is W transpose. So if I am in state W, then the next step also I will stay in state W. This is how I formally define a stationary distribution. It is one eigenvector for M transpose. Remember the definition of eigenvectors and eigenvalues? W is a eigenvector of M transpose with eigenvalue 1. That is what we call a stationary distribution. And we will also show that irrespective of mu 0, in a long run, mu 0 Mn will tend to W. It does not depend on mu 0. Remember that we initially gave the intuition that stationary distribution is the fixed distribution where we move to. And here we are defining stationary distribution as one eigenvector. But by the end of the proof, you will see that both the definitions have actually coincided. The one eigenvector, that is one definition, What distribution we converge to, that's another definition. But both of them are going to be same in the case of Markov chain. And that's why we are calling both of them as the stationary distribution. The formal definition of stationary distribution is this. So how do we prove that we tend to the stationary distribution? Not surprisingly, we have to look at the behavior of m to the n. Actually, it is better to look at the behavior of q to the n, where I define q as m steps of the initial Markov chain, because now I know that every entry of qij is positive. The long time behavior of m and q should be similar. If I just multiply by a constant, so q to the n is m to the nm, and since n is tending to infinity, both these behaviors will look the same. So I'm going to look at q to the power n. This is the most important theorem, which will show that q and y is going to be a constant. There's a difference between a constant vector and a fixed vector. Constant vector means that this is going to be a vector whose every entry is same, though the entry can depend on the vector y. Okay, so this is a constant vector. Every entry is the same. It is not fixed vector. But this is surprising that everything goes to a constant vector. But this is not the abelition of a Markov chain, because I am multiplying on the right. In the case of Markov chain, I multiply it on the left. So this is not the abelition of Markov chain. I'm just looking at the behavior of q to the power n. And this actually should not be surprising. What do I do? You can prove that every row of q is a probability vector. That means all entries are non-zero and sum to 1. If this is true, when I multiply by q to the q times y, I'm basically averaging out entries of y. So y itself was a probability vector. When I average its entries, all the entries come closer and closer. Let's say the maximum entry was m0 and minimum entry was m0. Now if I look at qty, the maximum entry will be mt and small mt. What I want to show is that this is much smaller than m0 minus m0 as t tends to infinity. So again, the intuition is that q averages out the entries. I will not go into detail. At this point, you should prove it as an exercise. If not, you can just take a look at the notes. It's a 4-line proof with the same intuition that since the entries of q are a probability vector, they average out the entries of y. So in every step, these quantities, so you will be able to prove that m1 minus m1 is less than some constant times m0 minus m0. This is less than 1. And you keep doing this and you'll see that it will become smaller and smaller. So my advice is you try to prove it formally. If you can't, take a look at the proof in the notes. This is good enough. We have proved that mn minus mn is going to be c to the n m0 minus m0, where c is less than 1. This is showing that as n tends to infinity, the maximum entry and minimum entry are tending to 0, which is same as saying that q and y tends to a constant vector. If the maximum entry and the minimum entry are the same, that means all the entries are same. So this proves a theorem. And this almost proves what we need. I'm going to give an informal argument, ignoring the limits, to prove that the regular Markov chain converges to the fixed vector. Using this theorem we have just proved. Remember that q and y is equal to cy. This is the all ones vector, boldface 1, for all y where y is a probability vector. This was the content of this theorem. And remember, cy can depend on y. Once I know this, going back to m, nm will be making things unnecessarily complicated, so I will just replace them by n again. It's a variable. So let's assume this, that there is an n, there is a big enough n so that m and y is equal to cy1. It's a constant, and this actually tells us a lot. You just fix y as basis vectors. That means, remember ei, it's just 0, 1 at the ith place. So if you place y as the basis vector, then mn ei gives you the ith column of mn. So this is saying that my ith column is a constant vector. If I want to look at mn, all the columns are constants. So this is c1, c2, c comma. All columns are constant. There might be different constant vectors, but this implies all rows are fixed vectors. You see that all rows are same. C1, C2, Ci, C1, C2, Ci, C1, C2, Ci. So all rows are same. Call this vector W. What we were able to prove is all rows of m to the n look like a fixed vector W. And not surprisingly, this W is going to be our stationary. If y is a probability vector, then m and y, you can easily show that if all the rows are W, then y transpose mn is going to be W. Whatever be my starting vector, if you want to know it by mu, then mu transpose m to the n is going to be W. Because every row is a fixed vector W, mu is a property. So this shows we always converge to W. The only thing remaining to prove is that we have W as the stationary distribution. That means formally it's a one eigenvector. M to the n plus 1 also will satisfy the same thing. All rows of m to the n plus 1 are W. This is not hard to show. You can take it as an exercise. So now W is equal to W transpose mn plus 1 is equal to W transpose m to the n, m is equal to W transpose m. So this shows that W is a one eigenvector for m transpose. It's a stationary. This completes our goal. We are able to prove two things. The W is the stationary distribution. That means there exists a distribution such that W transpose is equal to W transpose M, the existence. And second thing is, irrespective of mu, mu transpose M to the N tends to W as M tends to. A regular Markov chain has a very nice behavior. In the long run, all of them converge to a state. And thing which is important is that there exists a stationary distribution. This ends our lecture. We will see in the next lecture how to use it in computer science. Thank you.